In this next problem, let's actually go ahead and build the differential equation model for it. Now I know it's going to be really, really tempting for you to actually solve the equation without writing the rate of change, but eventually that will become impossible or very, very, very difficult. So we want to start thinking in terms of rate of change. Suppose that at any given time, water flows from a faucet into a bathtub at a rate of 8 gallons per minute. Assuming the tub is initially empty, how much water is in the tub after 13 minutes? So let's start off with our modeling process. We first define our variables. So it seems like what we want to keep track of, our y variable, you don't have to call it y, but we want to keep track of the amount of water in the tub. So water in tub, measured in gallons, and t will be time in seconds since we begin filling up. Since filling up begins. Okay, let's think for a second about what the meaning of dy dt would be. So because y measure is measured in gallons, we would have change in gallons divided by change in seconds. So the units of dy dt are going to be gallons per second. But that's exactly what we're given here. We're told that the tub, the rate of change of the amount of water in the tub, it's gaining 8 gallons per minute. So this equation, believe it or not, is simply dy dt equals 8. dy dt again keeps track of at what rate is the amount of water in the tub changing at any given second. Well, it's always filling up at the same speed of 8 gallons per minute, so there's no variable to go along with this. It's simply constant rate of change. And if you were to plot this constant rate of change function, if you were to graph dy dt for any given time, it would be a flat line at 8 gallons per minute. It's always filling up at the same rate. So what we want to know is that we want to ultimately know what's the total volume, right? So if you multiply gallons per minute, times minutes, you're going to get total gallons. And so we're going to do a lot of dimensional analyses here. And anytime we're talking about finding areas, that's the purpose of what integrals do. They accumulate area for us, at least geometrically. So to solve this, I'm going to take the algebraic step here. I can also ask, okay, if I want to know the amount of water in the tub, and you may already have jumped to this. You're like, well, I don't need to solve this differential equation. I already know it's going to be 8t plus 13 or something like that, or 8t plus 0. But to solve this, let me go ahead and integrate both sides. So what I'm asking is, what function did I have to take the derivative of to end up with 8? Well, that same question can be answered by saying, what is the integral of 8 with respect to t? And that's going to be 8t plus c, and the integral of a derivative is the original function, and so we get y equals 8t plus c. Our initial condition is the ordered pair y at time 0 is equal to 0, right? So how do we know that there's initially at time 0, there are initially 0 gallons? Because assuming the tub is initially empty. The tub is initially empty tells us what that initial condition is. So to find out what c is, I've got to plug in 0 for y, 0 for t. And we do want to go through this process because eventually c will not always end up being whatever your y naught is. In this case, we do get c equals 0. And we end up with a final function, y equals 8t. All right, now we can answer this question. How much water is in the tub after 13 minutes? That's going to be answering the question, what is y of 13? And we could also write this as y of t. So I'll do that. Y of 13 is going to be 8 times 13, which is 26, 52, 104, I believe, 104 gallons. And you probably could have just figured that out without doing any calculus. If the tub's filling up at 8 gallons every minute, and you do that for 13 minutes, then it's going to have 13 copies of 8 gallons in there. And I use the word copies to emphasize that we're basically reproducing 8 gallons every minute.